So I have the pleasure of introducing Graeme today. For those of you who don't know him, I'm sure most of you do, or at least know of his name. He's been around the Australian science community for a long time now. He got his PhD from the University of Western Australia, we'll just say a few years ago. And that was on how plants exchange energy and why certain plants have leaves of the size that they do. From there, he moved to CSIRO in about 1971. And since then, he's contributed to over 200 scientific journal articles, largely on the global carbon budget and the climate. He served as Chief of Atmospheric Research at CSIRO for 10 years, from 1992 to 2002. He has a long list of awards, and we here at the college are honoured to have Graeme with us a couple of days a week at the moment. And I've had the honour of working with him closely for the last sort of 6 months, which has been a great learning opportunity for me. It's fitting now that he'll sort of come full circle on his PhD research, now looking at limits to bioenergy and bio-sequestration. It's never been more relevant than it is today. It's somewhat of a contentious topic, but I think it's important that we hear some of these sort of fundamental limits that we know. So without any further ado, Graeme.
Alex and I are actually doing some work on solar radiation trends in Australia over at a number of observatories that have been measuring for about 20 years. But today I want to talk about something that's interested me for quite a few years now, and it does reflect to some extent my background as being originally in biology, although I claim that most of my career has been in physics, but it is a bit of a return for me that I go into this. The talk is a bit of a mishmash of various things, some of which is just thoughts in a way about where things might go, and some of it's actually just been published. So we'll look at it from that point of view. Now, do I have to point at this, do I? Yeah, okay. So I'm going to talk about the proposition that we can use energy from biomass, or we can use the carbon from biomass for sequestration as part of what all of you will understand is being considered. A bit about the efficiency of biomass production, which is where my biology comes in, and the fact that land is used for a number of different options, and I'll look at some of that. Transportation, the argument is that at some point some of this stuff would have to be transported around, and the work that I'll talk about there is just been published. And then some miscellaneous issues that come to mind in trying to think about this problem. So the proposition is the one that everyone here will be aware of, and that is that plants convert atmospheric carbon dioxide and biomass using the CO2 and solar energy. We recover this by burning it in some cases, and humans have done this right through their history. But we're thinking about using this to offset energy production from fossil fuels and associated emissions. So either sequestration or the use of this to offset the use of fossil fuels. We store the biomass or its carbon, leading to the net removal of carbon dioxide from the atmosphere. And of course, we can provide jobs, alternative technologies, alternative jobs in a transformation of energy futures about which a lot of people here are thinking about and talking about. So what's the press the wrong one. So this is the way I look at the proposition, and it's deliberately complex because I think it is complex, and it's more complex than a lot of people have thought. And that is that even if you knew all of these steps were technologically possible, and they are, each one of these steps in this diagram needs to be considered from a number of perspectives, and I'll give you a little bit of that sense in this talk. That is, there are efficiencies and inefficiencies of energy exchange for each of these steps, as well as carbon, but there are also dollar issues across each of these steps that need to be considered. And at the end of the day, we cannot, or we should not, ignore the fact that each of these steps actually involves social and environmental issues as well. So ideally, and I'm talking really very idealistically now, we would like to evaluate all of these steps to know whether this is actually a good idea or not as we go forward. But as the biologist in me came to look at this initially, because I was very familiar with this number. All of my earlier work with CSIRO was on the global carbon budget. And so I was aware of this number is reasonably well established, and the energy content of that net primary production, this is the uptake by terrestrial photosynthesizing organisms, is about 2100 exajoules. And we know about the emissions of carbon, and we also know the energy required, we require. And so we can look at these ratios. These are the ratios, if you just take the fossil fuel component, of the carbon content that is in the fossil fuel emissions compared with that that's actually taken out of the atmosphere by photosynthesis. So this is quite large compared with the capacity of the whole of the terrestrial biota to take it out of the atmosphere. Alternatively, if you look at energy from an energy perspective, the percentage 3% of the energy in our primary demand that is actually taken up by all of the photosynthesizing biota. In the Australian perspective, it's better. These numbers are better. We're around about 5 or 6% for the carbon side of it, and about 7% for the energy side of it. These are approximate figures, but it doesn't really matter. It gives you a feel for the fact that actually the terrestrial biota is not infinite. It's quite finite. And that what we're doing in terms of actually altering the carbon cycle in this regard is significant, whether we look at it from an energy or a carbon perspective. And this published a few years ago now, but was an attempt to try to say, well, what does it really look like in terms of individual countries? And this now is a plot of, for each of these countries, the percentage logarithmic scale of the use of energy over the net primary production. And so what it tells you is if you go to the US, China, and the United Kingdom and India, their primary energy demands are actually very similar to the capacity of all of their vegetation to take energy from the sun. So that, to me, raises severe issues, particularly when you look at the use of bioenergy in the US, or when you go to, as I did over quite a bit of my career, spend a fair bit of time in Southeast Asia, and find people enthusiastically talking about the use of their biomass, usually tropical forests, for energy. That's a concern to me. But there is this, we're of course is right, we're up here, as I said, around about 7% of the our primary energy demands of our capacity to, or our net primary production, our capacity of our biosphere to capture energy. Yet, and this is a very complicated slide, and I won't go through it all. The essence of this slide is to say, but despite this, there are a whole pile of people around the world very, very enthusiastic about the bioenergy issue. And in the previous paper I referred to, in the energy policy paper, I actually spent several pages in that document asking the question, why? Is it premature to be doing this? But if you go to the International Energy Agency, which some of you will know is not well known for its promptness in responding to issues, they are still arguing that we should be able to meet around about 2.5 exajoules from bioenergy as we go for, and I forget the exact time, it's something like the next 2 or 3 decades. But in energy terms, that is 12% of the content of the net primary production if it was converted with 100% efficiency from the biomass to what we need. And you know that if you shove stuff into a boiler, you probably get 30% efficiency. There are other processes. If you actually digest the stuff into get ethanol, you might do better. But there's inefficiencies in those steps that need to be considered. So this, to me, is something that they should be much more concerned about, promoting this. And are they doing a good job? Because Bioenergy Australia, here in Australia, this company is out there every day sending messages. I get them every day to people about their conferences, about their research programs, and in fact Australia's representation on IEA, because bioenergy is also bioenergy part of International Energy Agency. We have the biggest number of scientists involved in their program than any other country, and which I just simply can't understand. And I think it's simply because they're good at promoting the whole idea. And that's a bit of a worry for me. So what about the efficiency of biomass conversion? I won't spend too much time on this, but trying to think through it in my own way to look at where this primary energy production actually goes. It goes to producing components of the system, reproductive parts and vegetative parts. And out of it, it comes back here. And before humans existed, all of it came back here. The rest of the millions of species that shared the world with us, they had it all. And now we're using about 24% of it. So you can understand from that perspective partly why there's problems with biodiversity and the maintenance of some of these systems. And then there's a cycle up here, which is on-farm use of energy and so on, production of fertilizers, harvesting processes that affect that cycle up here. But eventually there's also tradable production. It's our food that comes out this end, or in the case of energy, as I say, humans are still using wood for energy. And the proposition in here that we have in this presentation is that we would put more out through the end there. So I'm going to look at a few parts of this. So my current research interest really that came out of that was to say photosynthesis actually is relatively inefficient conversion of solar radiation. It depends on the kind, and Alex is very familiar with this, the kind of plants, but most of the so-called C3 plants convert solar energy with an efficiency of around about 3.5%, and there are some plants that do it about 4.5%. And that's fixed by a number of things, including the fact that about half of the total spectrum, solar spectrum, falls outside the spectrum that the photosynthesizing plants can see. So you can't do anything about that, or at least at the moment, without massively modifying the photosynthetic process. and people are trying to do that, that's what we're stuck with. And actually, if you look at the 58 gigatons of carbon that's trapped globally, that actually represents about a 0.26% conversion of solar energy into biomass. So there are a number of actual other factors in an operating system that means you don't get the 3.5% efficiency finally in the products that you have on the ground. And there's a number of reasons why that, and I'll come back to some of that later. Global primary energy production is already about a quarter, which is what I said before, of net primary production. And for these countries, they are already very similar. If you take the extreme case of Singapore, small island, huge energy demand. If you cover the whole of the island of Singapore with photovoltaics, you won't produce enough energy. So as with Singapore, they don't produce enough water on their island. They also can't get enough food or energy. It all has to be imported. That's the reality. And it's already all right to be critical of that, but in fact, we sit in a city which is exactly the same. We only survive by importing water and importing energy from outside of the city into our demands. But that's the reality of the way we are. And even for Australia, energy demand, as I said before, is already about 7%. Now humans, and I'm not going to go into this too much, but people have tried for a number of years to say, well, how much do we actually already use of this net primary production? And numbers vary quite largely, and that's why I put 20 to 50%. The best number, I think, is about 24%, as it turns out. The research group that I'm most familiar with, and I think has probably got the best numbers. In other words, we've already imposed this leakage of net primary production into our system of about a quarter of what is available. So that is an impost on the rest of the millions of species that exist. Even for Australia, and I'm going to go a little bit more into these numbers in a minute, but 20% of our land is already in reserves for species and for heritage. If we assume, to start with, that we're not going to start eating into conservation or to heritage reserves or so on, that is a fixed part. So that the numbers that I was saying before in terms of what Australians are using is actually a bigger proportion of what's actually available. We're already using about 5% for cropping, and I'm going to give some details about that. At least 3% for grazing. I'll come back to that. I won't talk any more about bushfires. This is a number from Vanessa Havard's group in Canberra, and about 2% for energy. And then, of course, there are all the other things that we use land surface for. So the thrust really here is that not only are there severe limits, fundamental limits on what photosynthesis can deliver, we use and we will want to use what is delivered in a number of different ways. It's not just for energy. And so the idea is that we should be evaluating each of those steps. So that got me to thinking about the fact that at some stage, when you take, whether it be the leftover rubbish from the cutting down of trees in the Latrobe Valley or wherever it might be, or the leftover when you reap a harvest of wheat, you're going to have to move it to some place in one form or the other, either as the raw material or as some modified material. So I started to think about trucks, and I knew absolutely nothing about trucks, and it's good fun to do something like this, and it was good fun. And it's nice to know that, in fact, that's just been published this week. the study. And I'll come back to that in a moment. But here are estimates of the net primary production and utilisation on Australia. And here all I've done is to say, well, we know the area that's occupied by each of these things. And if we have put a nominal value on the net primary production in those areas, and for some of you this won't mean much, but this is the sort of thing that Alex would be very familiar with. These are approximate estimates of net primary production in terms of grams of carbon per metre squared per year. And then we use these areas, we can actually determine what mass of carbon is produced or what component of the total net primary produced is actually deflected by this particular purpose in either carbon or energy terms. Now this is very crude, but it's instructive to do this because the first thing you notice is that grazing, if you take the total area of Australia, which is 769 million hectares, the area that we graze is over 400 for sheep and for wheat, for sheep and for cattle. So it's an enormous impost, but very, very difficult to know exactly how much of the net primary production that grazed area is actually diverting and whether you could do other things at the same time. And I'm sure you could, but I don't know how much. I'll come back to that in a moment as well. But you can see, for example, down here, conservation heritage is a reasonable number of this total because the area covered by Australia, by that area, is about 20% of the Australian area. The good thing about this is it's a mixture of good productive land, and you can see I've put actually a fairly low figure on this, but a lot of poorly producing land, relatively desert areas that are occupied by or conserved for Aboriginal groups or whatever. The efficiency, however, I've looked at all of these systems, some of them globally, but here I'm only going to present the Australian data. Again, going right through, looking at the area available and looking at the actual production figures. So now we're looking at something that's slightly different. We're looking not at the net primary production of wheat, but what finishes up at the dock as wheat grains to sell. And that's not all of the production, because you leave about a third of it behind in the roots and about a third of it behind in the stubble, and you take about a third of it to market. But when you do that, what you're finishing up with, this is the percentage of the stuff, of the solar energy that fell on that area of wheat in Australia. So you see that all of these numbers, or nearly all of them, are around about, or they're certainly of the order of 0.2, 0.3, 0.4% of the solar radiation. So if you're actually going to sit at some part and import any of these things in order to produce bioenergy, you're actually taking out of the system something that is only 0.1, 0.2, 0.3% of efficiency of the solar energy that you started off with. And that's okay. We do that. People burn wood. I burn wood actually at home myself, simply because I can't get gas in my house, and I happen to have a lot of trees that keep falling down. So people still do it, but that's the reality. There's some differences. This one here I'll point to, because if you take just the sugar, and I've changed this overnight, because if you take the sugar cane, a very large percentage of sugar cane grown is actually harvested. You leave some in the ground, but most of the rest is actually harvested, much more than for many of the other crops. But if you only take the refined sugar, then you finish up with numbers very similar here. So the sugar industry, in terms of the sugar that's sold as refined sugar, also has these similar sorts of inefficiencies associated with it. Now, I said that trying to estimate the impost of cattle and sheep is more difficult, and some of you may be able to help me with this. And the reason is that we know that large amounts of cattle herding in Australia is you release cattle out into natural vegetation, and you know, after a few years you go back and catch them and sell them. And what you have no idea is that how much of the net primary production of that ecosystem was required for you to do that. It's clearly not 100%, but depending on if you read the literature, some people will argue that the reality is, in order to maintain a viable ecosystem, you need it all, and that this is part of the reason why, once you actually move cattle off land, there's quite a massive rebound of the ecosystems. But we don't know. If you just look at the displaced net primary production, which is what I did in the earlier table, it says that this number could be as high as 70%, and remembering that cattle and sheep graze nearly half of the total area of Australia. So this, if that was true, this would be a killer. I don't think it is. So I've calculated the metabolic needs of cows and sheep just standing, which you can do quite easily. And that gives you a number which is quite different, about 1%. Some colleagues have provided me with dry matter demands for sheep and cattle. And when you use that, I think this is a much more realistic figure. If you use that's the stocking intensity. If you use dry matter needs, it's only 4%. So it's somewhere in that range, and it's not very helpful, but that's where we're at the moment. I've even done it with feral animals, and this is just metabolic demands. So that if you look at feral animals, and these are approximately the numbers that exist in Australia, and they come and go a little bit because they do have expeditions to shoot these things. But on the basis of these numbers, it's about 1/3% of Australia's net primary production. These things are a nuisance there anyhow. You really don't want them because they cause biodiversity issues. But they're also using a small part of our national net primary production. And I've regarded that as a human impost because it's totally different from kangaroos. These are animals that we introduced, or human population introduced, and this is an impost on the natural net primary production. So if we start to try to summarise these, I'm not talking much about wood, but I've done forestry products as well. You can see that these numbers are of the order of a fraction of a percent for each of these various areas, remembering that cattle is extremely unknown, could be significantly higher, but conservation is large because we have this large area. So overall, we're talking about 1/4 of our net primary production is already appropriated by us. So it's not all available. And we then have to decide, which many people don't spend much time, is thinking of where we're going to be in 10, 20 or 30 years' time in terms of total population, food demand, and the other demands that fall in this group. So it's not just about providing energy, it's about providing other things. There are other issues like how much land do you need if you are actually going to use these different forms of capturing energy. This is a logarithmic scale, and I'd have to go back and check, but I think I used a 20% efficiency figure here. This is to actually replace a 1,000 megawatt power station. And the Sydney Harbour area is just put there for reference. But we go out here, wind farms are interesting because they do have a density requirement at the moment. Wind turbines are usually placed at 7 diameters from each other. There are some arguments within the literature that they should be further apart to maximise efficiency, but that's what the rule of thumb is at the moment. And then if you go out to natural or crops, that is what's actually left over down the, after you've actually moved stuff, then you finish up with this escalating demand on land, and land costs money. So you actually have to insert this into consideration. Are we prepared to actually do these things when there has to be a return on investment for the land that you're actually occupying? And of course, everyone here is very familiar with BECCS. And I think we are all interested in it because virtually everyone in this room, I think, would be concerned that we probably not going to be able to cope without having negative emissions going into the future. And so BECCS is one possible way of doing this, and it's attractive to those of us who seek to return recover carbon out of the atmosphere. It was very strongly supported by the IPCC working group, especially the special report that they did on bioenergy, which frankly I think was one of their worst reports. It was nowhere near as rigorous as IPCC I think had been in other places. It's supported by IEA, as I've mentioned before, but I got particularly attracted because the UK Climate Change Committee is a very high power committee. I think they've got something like 3 Nobel Prize winners on the committee. And they had actually contracted to have a report done to look at what bioenergy could provide it. And the study group determined that they were not going to meet the UK targets without bioenergy, and that they would need it to be of the order of 10% of the primary energy demand, which is equivalent to about 200 terawatts. Now it turns out, when I looked at this, that I'd already looked at the net primary production for the UK for another study, and it turns out that in the UK, they already appropriate about 52% of their net primary production. Ours is about a quarter, there's about 50%. A small country, large population. And in order to reach this target, they would actually have to appropriate 31% of everything that remains, all of the rest of the net primary production. It's not possible, simply not possible. And so I actually wrote to the committee and explained this. And I think by the time they got the report, they weren't believing the report anyhow, but it had been contracted. But something I hadn't realised at the time that I did that was they are already importing trees. So they're importing trees from the US and from Scandinavia in order to meet their requirements to lower their total emissions, because it doesn't count. It's counted, but it's counted as a zero emission because they argue, of course, that as long as you're using biomass, it's a zero emission process. Of course, ignoring the fact that you have to ship them across and the ship emits stuff, and you have to handle them, you've got to truck them around and all that sort of stuff. But this is not a good idea, but it shows you in the UK both the way the regulations, the international agreements are written with regard to the use of biomass, and the fact that they are hell-bent on actually meeting some fairly rigorous targets means that they're doing this. And let's hope we don't get too many countries doing that. Otherwise, our tropical forests will go very quickly. So I'm coming back now to this whole idea. We need efficiency of the full value chain to be assessed, from harvesting, transport, tree treatment, conversion, transport to utilisation. All of those things are in that rather funny coloured slide earlier. We also need, and I'm not going to spend time on this, the recycling of non-recycled elements like nitrogen and phosphorus, because when you take biomass off of a farm, whether it be wheat grains or stubble, you remove nitrogen and phosphorus. And of course, farmers know this, they've got to then pay money to put nitrogen back. And so without considering that as part of the proposition, you can get yet one screwed idea about what might be happening. You have to consider the cost of the land. In terms of energy, you have to consider the thing in terms of energy, carbon dollars, and so on. That's what the diagram was showing before. So I won't go through that because I'm going to diverge now and spend a little bit of time talking about my favourite topic of trucks. When I stopped to do this, I was naive enough to think and do the calculation thinking, well, if I want to shift some carbon from a wheat field to a processing plant, I know how much petrol. I've actually talked to guys on the main road filling up their trucks with diesel to get an idea of what their usage rate was. And then, of course, I started to realise that actually fuel is only a small part of their costs. And I finally found a guy who had done a PhD on exactly this subject. The companies would not give me the information. So I spent a lot of time with Lynn Fox and companies like that. And they were all very helpful until the bottom line. I needed to know what it cost to move a mass per unit distance. And they wouldn't tell me that because it's too competitive. It's a very competitive field and none of them would do that. So I had to calculate it myself. And I've done that for a range using the help of this, PhD person for different truck sizes. And the bottom line is out here. The dollars per kilometre per tonne from very small trucks is 53, ranging down to the big ones, 0.15. That's why we have big trucks on the road. And if you go to trains, it goes down by about another order of magnitude. I have looked at that a little bit, but not much. And I imagine ships is also maybe another order of magnitude on that. Relatively cheap to move stuff per kilometre per tonne. So what I've done, and you'll see it in the next couple of slides, is compared these big trucks with these small trucks. So these are 12, 16 tonnes trucks. Reasonable sized trucks, but nothing like these ones. And the interesting story about that, personal story, is that the moment I started to do this, of course, when I'm driving around Melbourne, I'm looking at trucks. And I became aware that this truck size was the common big truck, carries around about 40, 45 tonnes of payload. And in the 12 or 18 months since I started doing that, some of you will have noticed that these things had actually 6 axles, 32 wheels. They're on the road now in Melbourne. There are dozens of 9-axle trucks with 34 wheels, and they can carry about 60 tonnes. Why have they done that? Because this number will have gone down. That's why they've done it. Whether it's a good idea, of course, whether they're paying enough road tax, because the loading on each wheel is about 4 times the loading on the wheels of my car. So one suspects that they might be doing a little bit more damage than my car on the road. But that's the reality. Okay, so let's actually have a look at how that works out. So we now actually have transport costs per kilometre per tonne against the distance that we're trying to move. Simple linear relationship for the rigid trucks and for the articulated big trucks. Okay, so it shows you, for example, if you go 1,000 kilometres, it costs you as much as the carbon price at $100 per tonne of carbon. If the carbon price is more realistically down here, then you can only go a couple of 100 kilometres before you lost all the value that you would gain by actually someone saying, well, we'll pay you this price. That's the market price for the carbon. Or similarly, it tells you that if you've got wheat and you use this side of truck, you can't go 800 kilometres with it before you lose a lot of the wholesale value of the wheat. And so there's a combination of trucks and trains used for those areas. So it tells you quite a lot about that. But this is perhaps more interesting, and this is now the same thing, transport, but per unit of gigajoules. How much energy do you, how many dollars do you need per gigajoule? And this is only now for the big trucks. So it says that if you're moving lignite that has a high amount of water in it and relatively low energy content, therefore, that you can only go about 250 kilometres when the total value of what you've moved is equivalent to the retail price of petroleum. Now the interesting thing there is that the sugar cane is very similar because they both have around about 30% water in them, and so the slope for sugar cane is up here as well. And that's the reason why people who use sugar cane for fuel do it on the farm. That's why we burn lignite in the Latrobe Valley, because there's no value in moving at any distance. If you take thermal coal, then it's better. You can move it out to about 600 kilometres before it equals the traded value of thermal coal. So if you're trying to move thermal coal 600 kilometres somewhere like the Adani mine to the coastline, you know that transport by trucks is going to remove most of the value of the coal before you get it on the ship. And that's why you have to have a train to lower that by an order of magnitude, approximately an order of magnitude. So it tells you quite a lot. Even for petroleum, you know, if you have to go 2,000 kilometres, and there are parts of Australia where you have to go a fairly significant distance to get petroleum to Alice Springs for use there or something like that, that's the component of the retail value of petroleum that you've lost by going that distance. Now, you can read that, you can look at that diagram over and over again, and you can see all sorts of issues arise in terms of the relationship between the value of things and how far you have to move them. So now a few miscellaneous things just to finish off with. There are a whole pile of other things that I'm not going to go into, but the Nuffield report actually is where I've got most of these dot points from. But they've made the point that going into biofuels shouldn't be done at the expense of people's rights, whether it be land rights, work rights, health rights, whatever. They should be environmentally sustainable, and the word sustainable to me means long term. It's not what you could get out of the Northern Territory by mining gas today, it's what the potential for that is in the longer term, the impost of that in the longer term. Contribute to a net reduction in greenhouse gases, yes. Not exacerbate climate change, we'd all agree with that. Have trade principles that are fair, we'd all agree with that. And have costs and benefits distributed in an equitable way. Well, you know, just stop and think about what that means in terms of the way energy's been traded around the world, and has it really been done in an equitable way in this country or many other countries. Another miscellaneous point is to try to put these things into a bit of perspective. I try to do this with a few school kids actually, to try to get a feel for where things lie. Now, this is the amount of solar energy falling on Australia, and then we have to go down 1, 2 and a bit orders of magnitude to get what is photosynthetically captured. And this is what we use. It's around about an order of magnitude less than what photosynthetically is captured. This is what cars do. This is the energy in these crops. Now, why have I put this up? I simply want to indicate that if you wanted to actually use, say, a wheat crop or wheat crops to provide energy for the consumption of cars in Australia, you would have to have an industry as big as the whole of the wheat industry, which is something like 35,000 farms, with train lines, with silos, and all of those things that go to do. Whoops. To deliver this stuff. So, and there you've got to assume that the efficiencies of transport are transferring the energy to a liquid fuel that you can put in your car is 100%. Well, it's not going to be that. Aviation is similar. It's down here. So even just to meet aviation needs, it's going to be very demanding. Despite this, Qantas and a number of other companies around the world are desperately trying to actually increase bioenergy into their fuels. But if you actually look at the fine words within their statements, they're not silly. The fine words is that they will contribute to their fuel needs, not that they will replace the fuels that we have with biofuels. They don't say that because they know it's not going to be possible to do that. Just a couple of final points, because this is what I think is very relevant to this problem, but it's relevant to a number of others. And that is, the Gardner hypercycle says that there is a time issue here, that someone dreams up a very good idea. It sounds fantastic. It's going to solve problems. It's going to generate jobs and so on. And so there is a rise in the visibility. It becomes something the newspapers talk about, that ministers talk about, and so on. And then at some point, because what's happening during this period is that there is a growth of rigorous information, evidence base, that starts to say, oh, hold on, but what about the sorts of things that I've mentioned with regard to biofuels? Is that, and we hit a point where we have seen that our expectations are inflated and they drop away and into disillusionment, and in fact can go bang, and that's it. Or through enlightenment and new technologies and so on, we can reach a point which is usually below where we anticipated we were going to be initially, where we can see an ongoing benefit of doing what we can. So I think it's important here that to realise that we have unjustified enthusiasm, hype, followed by an onset of evidence base and then a collapse. Can be attracted to ill-informed people, but it can be wasteful of resources. And that is my worry about the bioenergy issue. Yet demand rigorous attention for their potential. So What I'm not saying is people shouldn't be investigating bioenergy. Definitely not, any more than, say, investigating carbon capture and sequestration. The point is to have some sense of realism around the level of knowledge we actually have at the moment with regard to these issues. I've spoken for long enough, so I won't spend too much time. The thing that really riles me is the arguments around algae, and that was really brought to a head when Tim Flannery wrote his recent book on the use of algae, because several of us, including Alex, have looked at the fact that his claim that somehow or other these algae are super capable of actually capturing energy disregard the fact that they use basically very similar photosynthetic mechanism. There is no reason for believing that they should be that much different. And in fact, if you do simple calculations by looking at the wheat yield of the world over the area that's using wheat, you find you get very similar rates of production. His turned out to be about 600 grams of carbon per metre squared. The global wheat production turns out to be 500. Experimental data with kelp turns out to be in this range. There's no evidence for what was actually stated in that case. Again, it's about hype in the absence of real solid information. And I won't go through the slide at all, other than say a very common thing that one finds when you're dealing with documents looking at the use of bioenergy is the use of the word wasteland. Somehow or other, the interpretation is that if you look out into Central Australia and there's nothing happening there, in your eyes, then it's waste. Well, the reality is, I take it as a biologist, a very different view. Every part of the land is occupied by an ecosystem. And that ecosystem needs to be considered, whether it be in its economic value, but also in its intrinsic value, as to whether you actually want to remove it. But it's a very common word that's used in the newspapers because it denotes the idea that we can do something and we're not going to have any effect. Well, that's not true. The moment you engage in any of these things, you will impact on existing ecosystems. Finally, and I'm raising this mainly for the PhD students here, because many of you will be tracking down here, a rationally, sexually defined description of the real world. You'll be trying to look at a particular area of expertise and define from evidence what might be useful in policy development down here. And what my talk has really been about is to say, but there's got to be a parallel piece here, because sometimes only knowing that one dimension is not enough. You actually have to know other dimensions, holistic dimensions, and people realise this, and that's the reason why we have groups like this that are quite a mixture of people coming at things from different angles, and that's very good. But there's a limitation to the way we actually practice science if we do too much in this and not enough in this. And where the balance is, I don't know, but it's worth considering. The problem for us in the climate change area particularly, but also in energy futures, is that the vast majority of our time, each of us as individuals, but the public's time, is in this mode. We construct the way we think the world is, not based on evidence. And we do that because we've been told that this is the way the world is by our parents, our teachers, and so on. And it's this constructed view that can be actually a non-reality view that influences policy development. So these things are going on in parallel. My concern is that we might be losing out. You know, the non-reality world becomes dominated by what people think they want the world to look like. I'll miss that one and just draw these conclusions. Bioenergy, needs to be evaluated in terms of the full value proposition. Technical and economic feasibilities, something that I get particularly from the Academy of Technology and Engineering, constant arguments with these guys, because many of them, I shouldn't generalise too much, but many of them believe that if you can do it, do it. If it's technically possible, why aren't we out there doing it? And that's simply because in some cases, not even with a proper economic assessment, but certainly not with social and environmental values and disvalues, or the efficiencies with regard to energy and carbon. There are trade-offs with other human, non-human uses of biomass. Just a few of them I've tried to raise today. And relevant to this and other issues are the concept of the hype cycle and strategic liabilities. The fact that the hype cycle itself, but many of the decisions are being made at the moment without this longer term component in there that says, yeah, it's not only just about what's going on now, but what finishes up in the longer term. Human behaviour and government processes are important parts of it, and the way science is conducted. Thank you. Sorry for going on so long.
Thanks so much, Graeme. Fantastic talk, very insightful and somewhat provocative. Food for thought, without a doubt. We'll take some questions now. I think we have one from the webcast that maybe we'll get set up, but we'll take some from the crowd. Could you please just give your name and your affiliation before your question? Thanks.
Thank you. Is it really? Can people hear me? Okay, Bill Graham, a retired ag scientist, and I'm sorry to say with an ageing brain, so a fair bit of this went over the top. But I was at another talk here at Melbourne Uni a few days back, chappie from ANU, and he was looking at taking account of our madly increasing population and our ambition to limit the carbon dioxide going upstairs with the objective, of course, to limiting the temperature increase and the need to feed these people. The equation just appears, as I interpret, he was judicious with his comments, I interpret that we've lost the game already. We've either got to relax our ambitions on global warming, and it in itself has negative impacts on the ability to feed ourselves, or we anticipate various degrees of malnutrition, starvation. You've probably given that some thought yourself.
Yeah, I have. I mean, to me, the climate change issue is very complex because it involves the sorts of things that these guys here were doing with me at CSIRO. So we were looking at the climate system and understanding as well as we could how that worked, and then the impacts that resulted from the kinds of changes that are being anticipated. But underpinning that, and what I've done mostly since I left CSIRO, is look at what's driving that, which is primary, not only the energy cycle. But if you go back before that, what's driving that? Population and GDP, or in some cases it's aspiration, if you like. It's humanly based. So I think you're absolutely right. But when you start to think about those things, I think it comes down to then whether you're really very optimistic or pessimistic. And I've decided that I'm an optimist. I have to be. I feel I have to be. But there are serious problems. I can't understand why Australia is continuing to have this very open, laissez-faire idea about population growth, for example. But it's a global problem, clearly. But I think you're right. It's an underlying issue for all of these things.
Webcast question, should we?
Yes. Michael, are you online?
Can you hear me?
Yes, we can hear you.
Okay. Like the previous questioner, an aging brain, but one of your earlier slides, I think you had called it page 5, comparing MPP with emissions and primary energy consumption. I just found it fascinating, but even the concept of NPP was a new concept for me. So I'd be really appreciative if you could actually talk through that slide again, and perhaps more as a student rather than a scientist. Thank you.
Can you get it back? Yeah, actually, I did think about this before I gave the talk. Certainly, most people in the community won't know what NPP means. That's true, but it's basically, it's the net removal of carbon or energy from the system after the organisms that are doing it have accounted for their own needs. So it's the available, and that's why it's called net. It's what the available material is after these photosynthesizing organisms have actually used the energy and carbon that they need for themselves. And as I said before, all of that was then what was used by the millions of other species, whether they be bacteria, fungi, or tigers, to actually survive. And since we've been here, we're siphoning off about a quarter of that energy and carbon for our own use. Does that help?
He's muted, so.
Oh, okay.
Question down the front.
Barry Piddock, former colleague of Graeme's, and 80 years old and not following all that well. My prejudice would be that biomass as an energy source should be mainly from waste products, and disposal of waste has obviously become a problem with China not wanting to take a lot of our not well sorted waste. And it seems to me that the problem there is how to do it safely and without further pollution, without generating CO2 that goes into the atmosphere or unhealthy gases and stuff. I would have thought that was a priority for biomass use.
Yeah, I think the current issue over the disposal of waste is raising this issue for a number of people too, including a colleague of mine who actually owns a waste disposal company, and a very big one. And we've had this discussion. There are a number of issues. One is that if you look at the total amount of waste in Australia, it seems like a lot, but in terms of energy content, it's not big compared with our primary energy demand. But that doesn't mean to say we shouldn't do it, because anything we can do can maybe actually assist. The second problem is that most waste is wet. And like brown coal and sugarcane, it means that you lose a fairly significant amount of the energy content in just getting rid of the water in the first place. But we need to be looking at all of those things, and I would argue that just the same as the general points that I've been making here, and that is that don't stop doing research on these things. We need solid evidence that says, yes, this is a good idea in a holistic way, or it isn't, rather than having a senior minister putting up his hand after an issue in South Australia and saying, oh, I know what the solution is, and then you've got $100 million on the table the next day to do something. It's not the way we should be doing it, and that's part of the reason why I'm concerned about whether the whole concept of evidence-based is being taken as seriously today as it used to be.
We might just take one more question, and just thinking about time, but feel free to hang around after and continue the discussion. So one more question.
Hey, is this on? Hey everyone, my name is Max. Really thrilled to be here. My question follows on from the point there about what do we do about waste. I started a company called Zero Impact, which is collecting coffee and turning that into energy. It's a company in the UK that's been quite successful with that. My question is, in terms of an Australian context, where we are we ready for that kind of innovation here? What's the biggest challenge ahead for that? Thank you.
Yeah, I think we are, but again, the issue that would come immediately in my mind, at least, is the magnitude of what you can actually do. You know, these numbers that we're talking about here are enormous. To try to actually interfere with what we're doing at the moment, it requires an enormous response. I tried to point out that, you know, going down, say, the wheat farm, taking wheat or the products of all of our cropping means a magnitude of investment and operation that it currently has been occupied by about 25,000 or 30,000 farms. It's a huge investment. And so what you need to do is to try to actually grasp hard facts about what could be achieved and what niche that could play in both from an economic point of view, but also in terms of the total amount of energy that you could actually offset.
Okay, we'll leave it there. We'll feel free to, as I said, stick around and continue the discussion. I just have one announcement. We have lots of great seminars like this here at the college. And the next one coming up is Monday the 7th at 6:30 p.m. It's one organised by Beyond Zero Emissions, which a lot of you will be familiar with. And it's titled "What the Frack is Going On?" Looking at unconventional oil and gas activities in Australia, given by Tim Forsey.
And that's not here, that's in the chemistry building, so don't turn up here.
Chemistry, thanks for that clarification. I didn't have that. Yes, so the recording for this talk will be available online. Feel free to go to our website. Please join me in thanking Graeme once more.
Thank you.